Today we are here to share a story about how Zalando increased the throughput creation for product offer data by 20 times using Akka Sharded Cluster. And before we go into details how Zalando did that, let's understand why we did that and in what context we did that. To do so, let me introduce you Zalando. So Zalando is a leading fashion e-commerce company, started its journey in 2008 with Germany and Austria, and expanded to 23 countries by 2021. And we serve over more than 49 million active customers with 5,800 brands. And the growth of Zalando since 2018 until 2021 has been exponential, which was the catalyst in replacing the current system, and exploring and exposing the problems we had with the old system. So since 2018, Zalando has added 8 new markets, and with each new market, we add 4.2 million articles in each market, increasing our assortment. And in 2019, with one of the biggest sales events, Cyber Week, we needed to process 100 million price discount updates under 1 hour. And when we were load testing this and preparing our systems, we figured out that our systems cannot produce that much throughput, and we cannot support this 100 billion discount updates. The throughput for the old system was 13K events per second, and we required 50,000 events per second to process so that we could accommodate the Cyber Week needs. But before we dive into what was the problem, how we solved it, let's understand this terminology, product offer. What is product offer? The product offer is a combination of price, product, and stock information for an article. So considering this article, this Air Max 97 premium shoe, it has 3 information: product, price, and stock. Product information is same for all the merchants. This article could be sold by Zalando itself because it's stored in Zalando's warehouse. It could be sold by Nike or some other merchants, for example, Shoehead.dev. The product information is same for all of the merchants because it's like the description about the shoe, weight, the model wearing it, like all of those stuff. So no matter where you buy it from, you'll always receive the same shoe. They will always have the same images and everything. So that's why the product information is same. But price information, it's different for each merchant. Zalando could sell it at a different price than other merchants, and each could have their own stock units. They could have different stock quantities as well. So this information combined is product offer. So this particular shoe has 3 different offers, and there could be multiple more. And what the system did was it combined this information and created this offer. And the architecture looked something like this. It's pretty simple. We were reading stock data, price data, and product data that was published by 3 different teams in 3 different locations to us over Kafka, and internally we used SQS queues. We were reading stock information. For example, a stock event comes with 9 units. The application read it, processed it, and stored it in a sharded Postgres cluster. Fairly simple. Same thing, the price information came for the product, stored it in the cluster, and then the product information. Now we have a complete offer for one article. But again, if someone, let's say, buy 1 article or 2 articles, or someone returns, the stock quantity changes. And that will emit an event. So the article will receive a stock event. The application will read it, but now it needs to update it. So we will read the data back from the database, compare the quantities, and again write it back. And that's where the problem started. Because for each event, for each price, stock, and product event, we were reading this whole huge offer data from the cluster, which made our Postgres cluster ineffective because we were hitting the limits of the IOPS limits of the cluster. We could have improved it by further resharding our database, adding more shards, or just scaling it vertically, but that's not very cost efficient. We needed to find a better way. And we found it, we were playing around with certain technologies, and we stumbled upon Akka Cluster Sharding. And my colleague Abdel will walk you through now how we used Akka Cluster Sharding to improve the throughput.
So before we start, I'd like to give a brief intro about Akka. So Akka is a set of libraries to build distributed systems, but we're going to focus on 2 main aspects. So the main building block of Akka is the Akka actor, which is modeled based on the actor model that describes the distributed computations. And actors are basically objects that encapsulate state and behavior. And they communicate exclusively through message passing, right? So in contrast to method calling, message passing does not transfer the thread of execution. So a sender can send a message and then continue without being blocked, achieving more computation, while the other actor is processing the message. And the actors react to the messages sequentially and just one message at a time. They react one message at a time. However, you can have as many actors as the hardware could support running concurrently. And because it's only one message being processed at a time, we can keep the invariant of the actor without worrying about synchronization. So it becomes completely non-blocking. The other part is that everything in Akka is built to work in a distributed setting. So you can have multiple nodes. The actors can lie in any nodes of them. And Akka provides us location transparency, which we don't need to worry exactly where an actor is located. You can use just an actor reference, which is a logical reference to where the actor is. And then Akka will figure out how to deliver the message through the network. So keep in mind these two features of Akka while we talk about concurrency problems. So this is the old system, like as Rohit explained. So we can get updates. Here we are getting an update for the exact same product offers at the exact same time. And then the post will try to load the data, post we will try to update it in the memory. And then what happens here, the data is inconsistent, right? So, and to fix this, basically in the old system, we were working with Postgres, so we introduced a pessimistic lock on the database, which means only one host will be able to get an exclusive lock in a row, and then it will be able to update the data, and then the other host will continue and get the updated data, and then update it, and then put it back into the database. So the problem here is that was pretty slow. So the one of the thread of execution will block the others until it finishes updating the data. So that's one. The other part is that the database load increased to be able to maintain all these transactions on all of these locks. And there where we went when we started to design the new system, we wanted the system to be non-blocking. So we don't need to have any locks in our system. And with this, where the actors come in. So we created an actor for each database row that we have. So let's call these entity actors. This is how it's called in an Akka cluster. So each database row will have its own actor that processes all the updates through it. And in this way, if we received multiple updates at the same time, they will all land in the actor mailbox. So, and then the actor will start processing one by one. So it will process the first message, store it in the database, and then go on and so on and so forth. So what we gained in here is that we removed the lock completely from the database, right? But we also gained like another thing that the first time that we create the actor, it loads the state from the database once, and then it stays in the memory. So the data transfer between the application and the database became much less, and then we were able to process messages much faster. So that is one thing. But now, how do we fit all of these actors? So we created an actor for each product offer. So how do we fit millions of actors into the memory, right? So, and this is where Akka cluster sharding comes. So imagine that we have like many actors that we want to distribute among a cluster. So what we do is we first say it's like, okay, how many shards do we want to distribute these actors across, right? And usually, like a good rule of thumb for Akka cluster is 10 times the maximum number of nodes that you want in a cluster. So if we want to run the cluster with 100 nodes, then we will say, okay, we need 1,000 shards. And then we also supply Akka how to distribute these entity actors across the shards, right? And this is called sharding strategy. So it can be basically as simple as like hashing algorithm mod the number of shards. And then what Akka does, it's going to distribute the entity actor across the shards, and then it's going to distribute the shards across shard regions, which basically correspond to nodes. So each node will host a single shard region, and each shard region can host many shards that eventually host many entity actors. right? So now that we distributed the actors across the cluster, we wanted to start consuming the events and kind of stuff. So before we go into that, there is one special actor that we will need further that is called shard coordinator. And the shard coordinator is the one that assigns shards to their regions, and they are also it also knows where each shard lies in the cluster. So to consume the data, we introduced a different type of node that will not contain any shards. It just have two main actors. The first one is a polar actor. And a polar actor basically pulls the messages from our input queues in SQS. And then we have another actor provided by Akka. This is called shard region proxy. And this actor interacts as the entry point to the cluster. If you want to send any message to any entity actor, you will have to go through the shard region proxy. And the way it works is that we get a message, for example, for product one. And then here, the message goes to the polar will just forward the message to the shard region proxy. The shard region proxy at this time does not know where product one is, right? So it will go ask it will compute first the shard using the sharding strategy, and then it goes ask the shard coordinators like, okay, where does the shard one is? And then the coordinator will reply with the correct shard, and then from now on, it's just forward the message to the shard region, which will forward to the shard, and then it goes back to the entity actor. The shard region proxy has this feature where it remembers where shards are. So now if we get another message to a product that lies in shard one, it doesn't need to go and ask the shard coordinator. So it will just go through directly from the shard region proxy directly to the shard region and then to the entity actor. And now we currently have our system architected designed, and we wanted to run it on Kubernetes. And for this, Rohit will walk you through how we did it and other challenges that we faced.
So we wanted to run this Akka cluster. What is a cluster? It's a combination of nodes working together towards a common goal, right? And the nodes talk to each other to form the cluster. And a new node joining the cluster can say to some node, hey, I want to be part of this cluster. And the node can say, yes, you can be. But what that node is, for that, we have something called seed nodes. It's a special node. It's a special role assigned to certain nodes in the cluster that will be acting as a contact point. So each node, any new node who wants to be part of cluster can contact the seed node and say, hey, I want to be part of this cluster. And the seed node can reply, why not? And then this new node will join the cluster. And how Kubernetes helped us with this? So there are two requirements for a node to become a seed node. First of all, they should have a guaranteed ordering, and they should be deterministically discoverable. So any node who wants to become part of cluster, they should know, like, this is the node I want to contact. And Kubernetes provides us with two things. One is headless service, and another is stateful sets. So stateful set is a workload API provided by Kubernetes that manages pods and provides us with guaranteed ordering. So if you create a stateful set, it will create pods. For example, here, the application name is offer creation. So there will be pods like offer creation 0, 1, and 2. It has a guaranteed ordering. And to discover those, the headless service provides us with a URL that can be easily formed. The application name, the ordinal, the service name, namespace, and svc.cluster.local. So that's how we created our cluster with some predefined seed nodes. We said like node 0, 1, and 2 will be the seed nodes. But there are certain issues with stateful sets. And one of the issues is that if by mistake we deploy some faulty configuration or faulty pod template, the pod will never become ready or in running state. But stateful set will keep on waiting for those to become, and our cluster will never be ready. So what you do, you fix the template, you fix the configuration, but you also manually need to delete the pod so that it can progress with the deployment. And it needed manual intervention. That was one problem, but not the problem that happened very often. The another was Akka cluster runs something called cluster singleton. A cluster singleton is a special actor which runs only on a single node across the whole cluster. And it runs on the oldest node. So let's say our application has n pods. The stateful set will create the pod in sequence, in an incremental sequence, pod 0, 1, 2, 3, and so on and so forth until n. So this cluster singleton will stay on node 0. Now we do the first deployment. Stateful set will start the rolling update from the last pod. It will delete pod n, then n-1, and so on and so forth until 0. So this cluster singleton will be on the 0th node. All the pods will be rolled out. Then when the 0th node will be restarted, the cluster singleton will move on to the nth node because that's the oldest that was started first. And then you do the deployment again, you do the rolling update, this pod will be restarted. And the cluster singleton will, with each pod restart, will move on to the previous node. This causes like a huge disruption in our cluster. So the every alternate deployment caused this movement of cluster singleton. And that's what the problem with the stateful set was. But lucky for us, Akka provided us with a toolkit called Akka Cluster Bootstrap. And it works on the principle of contact point discovery. So we don't use stateful sets anymore. We leverage Kubernetes API. So there are a bunch of pods running in the cluster. They contact Kubernetes API and ask, like, give me the contact points. So after this contact point discovery, we will know what are the nodes in the cluster because with the service will provide us like all the pods that are part of this cluster. Now node 1 will start because we need to know the seed nodes, right? That's how we join the cluster. We need to know, hey, we need some contact point. Hey, I want to be part of this cluster. So node 1 will contact another node, the contact point, asking for the seed nodes. And that node will say, I don't know, because there are no seed nodes. We didn't define it this time like we did in stateful sets. And this happens for a certain time. But like node 1 is contacting node 2, doesn't get a seed node. Node 2 contacts node 1, doesn't get seed nodes. So what happens? We have this configurable time called stable margin. When this stable margin is passed, the node with the lowest IP address will join itself and form the cluster. Now that is the seed node. Then there is a cluster, but with just one single node, and it's called seed node. Node 2 will start, make the call again, like bootstrap seed nodes. Node 1 will respond back, yes, I am the seed node now, and then the cluster formation will start. That's how the whole cluster is formed. Now our cluster was running very fine. We were reading messages. The Polar was responsible for reading SQS messages from SQS queue and sending it to the shards, which were responsible for the processing, right? So with this AWS SQS, you read messages in batches. Each batch has a maximum of 10 SQS messages. So we read a batch, we forwarded it to the responsible shards, and our cluster was working fine. And each shard acknowledged each single message back to SQS because that's how it says that I have processed this message. But then the cluster ran fine for some time and it started to show some problems. It became unstable. So the shards were doing a bunch of stuff, storing data into database and then calling other third-party services and then doing other stuff. They were slow. Polar had one job. Read messages from SQS, send it to shard. And it was way too fast for shards. That created a lot of entity actors on the nodes. And some of the nodes just died because they went out of memory. And when the node died, the actor for each product, they were moved to a different node, and then this process continued. So this was a problem. There was no control how fast we were polling the message. Our consumer, the shards, were really slow compared to Polars. So what we did, we introduced back pressure. We wanted to control how fast we poll the SQS messages. For that, we introduced a parameter. Like we wanted to contain how many maximum unprocessed events in the cluster we can have. Right? We could say like we could have only 50,000 unprocessed messages in the cluster. And then we also wanted to have some pre-fetched buffered messages because we don't want to poll SQS queue every time a message is processed or a batch is processed because that's also an expensive call. And to implement this, we introduced a cluster singleton. Like I said, the problem with stateful set, the cluster singleton moves on. We introduced an actor, cluster singleton, that is the only single actor responsible for maintaining the polling. Its job is it will keep track of how many unprocessed messages are there in the cluster. So let's say if we have 100 messages that the cluster can process, it will pull 10 batches, and now there is 0 batches that it can process. And once it processes one batch of 10 messages, then we have 10, this maximum number the cluster can have is 10, and it will pull another batch. So that's how we controlled this whole thing, how many unprocessed messages do we want to have in the cluster. What it did, based on the parallelism factor, let's say the parallelism factor was 2, it created 2 child actors. Those child actors fetched batches or read a batch from SQS queue and sent the messages to the respective shards. And those shards processed those messages, acknowledged it back to SQS, and once the whole batch was processed, they will send an acknowledgement, yes, I have the whole batch is processed, and the SQS poller will kill itself. The child will kill itself, and now we have more unprocessed messages in the cluster, a new child actor will be created, and the process will go on. Right? So the cluster worked really fine now. We were in production, but after some time again, just didn't work. What we discovered, some nodes started to become unreachable from time to time. Not very frequently, but time to time. And why did it happen? And how did it happen? And to do so, we need to understand something called failure detector. So each node in the cluster runs a process called failure detector. What it does is, like a bunch of random nodes pre-configured, watches a single node and asks them, they send a heartbeat signal periodically and ask them, hey, are you alive? Are you still in the cluster? They will send a heartbeat signal to node 5, for example, in this case, and they will receive a response back, yes, I am in the cluster, I'm alive, and the cluster works fine. But if node 5 does not respond to any of the node, this node will be marked as unreachable because one node didn't see it as working. And this information will be spread through the cluster using gossip protocol. Why was this happening? Why was node being marked as unreachable? Why it was not responding to certain nodes? Because we were processing a lot of messages, a lot of string objects, JSON objects, price, product, and stock events, and we were creating a high GC pauses. So the application had really huge garbage collection pauses, which, like, for when the garbage collection happened, this node did not respond to anything and it missed these heartbeat signals. How did we improve that? I mean, we tried to configure the default concurrent mark and sweep garbage collector. It worked fine, but then we replaced the CMS with the G1 garbage collector and our application worked really fine. And also we did another improvement. We used compacted string objects, which reduced the memory footprint by 25%. And now finally our cluster was in production and running. But as with every system, you can always find things to improve. And there were further improvements that were done in the system, which my colleague Abdul will walk you through.
So before we start talking about batch queries, I want to clarify one of the main requirements for the system, one of the main constraints that we worked with, that we couldn't change the database that we are working with, right? So the new service had to run with the existing sharded Postgres. And for that, so when we first started, we had the actors directly calling the database. And when this happened, we had so many connections from all the nodes that we have, and started hammering the database really hard. And we needed to kind of like find an alternative approach to that. So the first thing that we did is that we introduced a single actor in each node that will communicate with the database. And the way it works, all the entity actors in there will send their queries to the DB actor. The DB actor will batch them, and then just like batch them based on which shards these queries are going to, and then just send the queries to the database shards. But we had a problem in here. So the database sharding algorithm, this is an existing database, right? So we were talking, it's been, I think, in production for like 7 or 8 years. So the sharding algorithm in the database, we couldn't use it in the Akka cluster because it has a limit on the number of shards that it can give us, right? And then we had to go with a different sharding algorithm for the Akka cluster. And what did this do? It made every actor in every shard host different actors that belong to different database shards. And for that, we had we had a very low patch numbers when we started patching. So we needed to change the sharding strategy. So the first thing that we did is that we split the Akka shards between the database. So each database shard will have only some subset of the Akka shards. And then afterwards, so we calculate the DB shard, use the DB shard algorithm. These algorithms are incorrect, so this is just an example. And then what we do is we calculate the position on each group. So if the first one said, it's like, okay, if I have the product that lies in shard 3, so the first calculation will return 3, and then the second one here will just return a number between 1 and 25, because each shard maintains 25 Akka shards. And then what happened at the end is that we just sum all the Akka shards before the database shards that we have. So here, it's gonna give us the number that lies through shard 3, which is something between like 51 and 75. At the end, what did this do is that we actually, if you see here, each shard from these shards will communicate only with a respective database shard, and this increased our patch queries a lot, and it's also increased the speed of processing, or the number of messages that we were able to process in the same time. What is the result of all of this? So this is what we wanted, right? So we wanted to achieve 50K events per second, but we actually ended up with a much higher number. So this is when we actually stopped load testing it. This is not what we don't know if we could have increased the number of that, but at this number we were just satisfied, so we stopped load testing in this. But there is also a very interesting thing that happened that we didn't account for. So the payload size for our events increased almost 3-fold because of how the Zalando business grew. We started to have way more offers than before, but the cluster will still maintain the same throughput. There might be some hiccups at the beginning with some parts in different application, but at the end we still managed to process almost 20 times the data throughput that we were processing before. So yeah, that's all the story that we wanted to share with you, and thank you for being here.